get started. Looks like we have. Oh, thank you. Oh. Why? Because this thing. Yeah, I see. I was recording without the microphone. Maybe that's why. I don't know if I'll notice if that happens again. That's true. Well, you'll have an advantage over that since you're in class. Alright, let's get started. We don't have too many of you. Maybe it's because of the weather. But you expected this, right? It couldn't have been right. So, snow tomorrow. Well, we didn't have any snow, so it has to be back. Okay, today we'll finish Runahead and we'll start another exciting topic, hopefully, which is multiprocessing, which is what pretty much all processors are today. But we'll start with the fundamentals of multiprocessing. But before that, hopefully you know this by now. You have a lab assignment due today, and I strongly encourage you to finish it by today, because the next assignment is already out. Actually, some of you asked for it before we put it out, but we had to make it easier, a little bit easier, before we put it out. So hopefully you'll enjoy the next assignment. Next assignment is on multiprocessing. Well, I'll just skip this. If you're doing extra credit, keep doing the extra credit. But next assignment is building a cache-coherent multiprocessor system. Basically, you'll implement the cache coherence protocol at the C level. And we will talk about cache coherence starting Wednesday. And I'll give you some readings on it. And the lab assignment is actually quite self-sufficient in terms of what you should implement. So you can learn about the cache coherence from that lab assignment as well. So hopefully it'll be exciting. It's due May 4th, but I encourage you to finish it earlier. Because the final exam is on May 10th, right? Yeah. Finish it as early as possible, basically. You can do an extra credit. This is not specified in the lab assignment, but I decided to add it here. Basically, you can improve the cache coherence protocol to make it better. Right now, the cache coherence protocol is the MESI cache coherence protocol, also called the Illinois protocol, because it was developed at Illinois. And it has 4 states. These are actually stand for states, and we will get to that on Wednesday. Or you can get to it as you read the lab assignment handout. How many of you looked at it? Good. Several people. Okay. Midterm 2, as you might have seen, they're waiting there. So I'll give this at the end of class. Please give me a 15-minute warning so that we can distribute the midterms. And maybe I'll go over a couple of questions also. Because I was actually surprised with one question. I thought everybody would get it right, but almost no one got a perfect score on that question. Hopefully, not in the final exam, that won't happen. Or something similar. Okay. Well, speaking of which, final exam is on May 10th. Do we still have color issues with this projector? It's supposed to be red. You guys see red? No, we don't see red. So let's turn on the right projector also and see if we see red here. Okay. It's going to be comprehensive. We'll talk about this later on also, but I'd like you to start thinking about this because this is perhaps the single biggest assignment in the course, right? It will be 30% of your grade, if I remember correctly. And we will have a review session. We'll try to figure out when to schedule it for. And you'll have 3 cheat sheets allowed. And I will take into account your improvement over the course. So if your trajectory is going up, that's a good thing. In the sense if your derivative is positive, you'll get a better grade. Oh, okay. I see. Yeah, I do want to change that problem. Where is that laptop? Do you see color here? worse? Yeah. All right, I'll turn this off then.
My life is in shambles.
Just go right to the picture, hopefully. Okay. Okay. And, well, know the previous midterm concepts by heart. And we will make the final exam shorter. So you'll have more time. But prepare up. Okay, this is a belated note. I wanted to discuss this earlier, but somehow I forgot. But we have taken into account your feedback, at least for those of you who have given feedback to us, which wasn't too many people actually. But some feedback was contradictory, just to give you an idea of what it was. Pace of course, some of you found it fast, some of you found it slow. But hopefully the videos helped. Some of you indicated that actually videos helped, even if you found it fast. Homeworks, this was a love or hate relationship. Some people really hated the homeworks. They thought it was a waste of time, but some people actually loved the homeworks because it let them study the concepts better. So I don't know what to do about that. But we don't have another homework. I guess for those of you who loved it, it's probably not a good thing. But you can go and study the previous exams, perhaps, or maybe we can put out some potential questions on coherence, for example, just so that you can study for the final. But it won't be an official homework. But it was surprising to me that it was really on the opposite end. Workload, this was actually surprising. I thought many of you would complain that this would be heavy, and you expected that it would be heavy. And some of you did complain that it was heavy, but you indicated that you were learning a lot too, which is good. But some of you actually, I don't know if you joked or not, but you found it very easy, so you wanted more assignments. Good thing it's anonymous, that I'm not announcing your name, so. But don't tell this around your fellow students, perhaps. Okay, but many of you indicated that you're learning a whole lot. I hope that is truly the case, and I hope that will, like a lot of the concepts we cover, will persist with you for a long time. Because a lot of these concepts are actually very fundamental concepts of computing in general, like multiprocessing that we will cover today is a very fundamental concept. And hopefully you will get the high-level trade-offs in all of these, even though you may not be able to finish the 20-page exam today. Okay? Readings for today. How many of you read this? I asked this earlier in the semester, I think. You read it? Or you're going away? That was what this was for. Yeah, this was before the beginning of the semester. Now it's a required reading. So if you have read it, you will not have to read it again, but hopefully you'll enjoy it. It's a 3-page paper, right? Or was it 2 pages? And also assigned a high-level reading on multiprocessors and multi-computers. This should be relatively easy. And we'll scan these and put them up on the AFS. And I also assigned the data flow and multi-threading just so that you can contrast these concepts with multiprocessors. This is a recommended reading, but you don't have to read that one. For Wednesday, we'll cover cache coherence. So these are your required readings. And well, of course, the lab handout should be your required reading also. But we have some recommended readings also, some seminal papers. This is the first paper that introduced the MESI cache coherence protocol, which is a variant of which is implemented in many processors today, actually. And this is the paper that is a 2-page paper, so maybe I'll consider making it a required reading. This is the first paper that how to make a multiprocessor computer that correctly executes multiprocess programs that looked into ordering issues that happen when multiple processors actually access memory, and how should that order be presented to the programmer so that the programmer can actually program multiprocessors in a sane way, so that when you write a program once, you don't get an order that's different from the next time. Okay, but we will get to that. Thanks. So last lecture we wrapped up prefetching. Hopefully you know all of these concepts by now. There are a lot of creative ideas that were related to prefetching. Content-directed prefetching being one of them, I think. We talked about execution-based prefetchers, of which Runahead execution was one example. So today we will wrap up Runahead execution, look at some performance results, and start the multiprocessing fundamentals, and talk about the cache coherence problem if we get to it, but probably not propose solutions. So remember what we were doing? We were talking about how do we tolerate stalls due to memory. We could reduce or tolerate the stalls. And there were 4 fundamental techniques, all of which you should know pretty much by heart now, right? And we were talking about how to do prefetching with Runahead, which approximates the performance of a large out-of-order window. Right? And Runahead was an execution-based prefetcher, right? The idea was to pre-execute a piece of the program solely for prefetching data. And you remember execution, thread-based pre-execution prefetchers. Okay. Runahead was not really thread-based. It didn't require separate context. It started pre-execution when you actually stalled for a load here, such that hopefully you would pre-execute the program and get to this other load and prefetch the data. So I'll go over this very, very quickly just to remind you what Runahead was. Remember, we have small windows. Now you can see the red better, I guess. I can see it better. It's still not good, though. Yeah. You basically, whenever you get a miss, the processor stalls soon after, and then during the stall cycle, nothing happens because the window is full. Well, the miss is serviced. And when the miss comes back, the processor can continue computation fetching instructions. And when another miss happens, the processor stalls again. With Runahead, instead of stalling for the first miss, when the load that caused the miss becomes the oldest instruction, we checkpointed the register file state on the program counter, entered the speculative processing mode called Runahead mode, where instructions are speculatively executed without updating the architectural state. And we talked about the invalid and valid values that are invalid values, or values that are dependent on the cache misses that are not available yet because you're waiting for them from memory and you don't use them for prefetching or branch resolution purposes. Right? And while you're running ahead, executing speculatively, hopefully you discover this load 2 miss because you weren't stalling anymore. And hopefully it's valid. Hopefully it's not dependent on this load 1 miss. And that means that you can generate its address and start the miss caused by it earlier such that you can service in parallel with the previous miss. And at the end of Runahead mode, basically flush the pipeline, go back to the checkpoint, which means that you set the processor sets the program counter to load 1, and the processor re-executes starting from load 1. And when the processor gets to load 2 during re-execution, that miss is complete. Now you've saved a bunch of cycles. Now it's not as good as perfect caches, but it's much better than the small window. Okay, so we talked about the advantages and disadvantages. Maybe I'll briefly remind you of these. You get very accurate prefetches because you're actually following the program path, right, when you're prefetching. It's simple to implement. Most of the hardware is there. You just need to add several things, and I'll let you think about what those things are. We discussed them, all of them. And compared to other pre-execution-based prefetching approaches, it uses the same thread context. There is no waste of context. Of course, there is still a trade-off, right? Instead of doing Runahead, you could switch in another thread if you had another thread context that was available quickly. So you could do coarse-grained multi-threading. And that's something for you to think about. What are the trade-offs associated with that, right? Switching a new thread has penalty because now you need to warm up the caches for that particular thread. Whereas if you do Runahead on this thread, caches are already warmed up. You can go faster. But if Runahead is not useful, if you're not going to discover another cache miss by speculatively executing, maybe switching a new thread is a good idea. The second advantage over other pre-execution-based mechanisms is that there is no need to construct a pre-execution thread because you're using the program. You're just keeping the execution of the program, except it's speculative. Disadvantages, and we'll get back to this a little bit later. We execute a lot more instructions now, right? We execute once when the cache miss is being serviced. That's a speculative execution, and you go back and re-execute again. And we talked about how this is limited by branch prediction accuracy. This is fundamental to a large instruction window, right? Whenever you would like to execute further ahead in the program, you need to predict your path. And if your branch predictor is not doing a good job, you can have a 2 million entry instruction window, but if you mispredict the branch, then a lot of the instructions can be on the wrong path. So you'll need to flush them and re-execute. And we talked about how to improve branch prediction with many different techniques. You cannot prefetch dependent cache misses, and we'll take a look at this a little bit later. And we had a conversation about the last two, so you'll remember. Now you can go back to the video if you don't remember also. Okay, so let's back up a little bit. I'll show you some results in terms of how Runahead performs. But before that, this is an execution-based prefetching mechanism, right? And execution-based prefetchers, we covered quite a few of them. Now, their pro is they can prefetch pretty much any access pattern. Right? Runahead, for example, as long as you don't have dependent cache misses, you can prefetch. In general, execution-based prefetchers, even if you have dependent cache misses, you can potentially prefetch things, right? Because you're constructing a thread, and that thread can be constructed even by the programmer. Do you guys know about skip lists? No? Yes? Some of you do? Okay. So, for example, if you want to prefetch a linked list, you could do things like this. Maybe prefetch ahead. Normally, when you construct a linked list, you have pointers like this, right? The nodes point to the next node. But what if you added another pointer here that points to a later node, right? And you have another pointer here that points to a further node also. Maybe you use these pointers in your speculative thread, pre-execution thread, and your pre-execution thread does this, right? It prefetches this node and then skips to that next node. And you could have multiple pre-execution threads doing this potentially. So there's a data structure that can be built using these pointers. I won't go into detail. It's called a skip list. That way you can actually improve the searches as well. You can actually use this as a programmer to reduce the amount of time it takes to find a value in your list. But in this case, you could potentially use that for prefetching as well. So that's one idea. So you can pretty much, if you have this thread, if you will, that you construct that does prefetching for you, you can pretty much do anything with it and prefetch any access pattern. So that's the biggest pro of an execution-based prefetching. They can be very low cost. For example, Runahead execution is very low cost. It doesn't add much storage or much complexity into the processor. But of course, they may require new thread context. But if you already have the thread context, an execution-based prefetcher can be low cost. Well, especially if it uses the same hardware context. Why can they be low cost? Because the processor is already equipped to execute the program anyway, and what you're doing is executing another thread, if you will. Can be bandwidth efficient. Actually, a lot of thread-based prefetching mechanisms can be bandwidth efficient as long as you're not going too far away. And it turns out Runahead execution is very bandwidth efficient also because you're prefetching through the program path, and you're not prefetching much farther ahead of the program, right? Your prefetch distance, if you will, is limited by the number of cycles that it takes to service limits. And you could actually adjust this bandwidth efficiency because, in a sense, you're constructing the thread to do the prefetching. Yes?
So when you use Runahead execution, you have a small instruction window, but you also need the Runahead cache. So what's the, what fraction of the space that having the larger instruction window does the Runahead cache correspond to?
Yeah. So read the required paper. But I'll answer your question. The question. So I required the Runahead reading. I'll tell you about that later on. You should look at that. But you can get away with a small cache. So there are several issues here. You can get away with a 512 byte cache, as described in that paper. But also, it's the complexity of the large instruction window. the cache, the store load, remember that Runahead cache is to allow the store load communication in Runahead mode. We discussed this last time. And that can be a simple index structure. Whereas if you extend your instruction window, that requires a complex tag matching logic. So it's relatively simple. Okay, so the downside of all execution-based prefetchers, including Runahead, is they depend on branch prediction and possibly value prediction accuracy. You could do this, for example, in your skip list, but if you skip too far ahead, maybe you're prefetching useless stuff, right? Because maybe the thing you're looking for in this list is around here. Okay. So in a sense, if you're skipping, you're kind of predicting that you will continue to that point that you skipped. And that's your branch prediction accuracy in this particular case. In Runahead's case, you have a branch that you predicted. If it's dependent on a cache miss, well, you're on the wrong path after that point. Okay, basically mispredicted branches that are dependent on missing data throw the thread off the correct execution path. Now this may not be bad, as we discussed, but it's usually better to be on the correct path. That's also empirically shown. Execution-based prefetchers can be wasteful, like other prefetchers, but there's a difference from other prefetchers, like hardware-based stream prefetching, for example, here. Those don't execute instructions, right? Those don't take up instruction processing bandwidth. Whereas execution-based prefetchers, they do speculatively execute many instructions, and they do exercise the core portion of the processor. So they're more power-hungry, if you will, potentially. And they can occupy a separate thread context when you actually need it. So this is bad when you actually need it. If you don't need it, this is good potential. So this is just to give you some results of how much actually prefetcher and Runahead affects performance. In this case, when I say prefetcher, it's a hardware-based stream prefetcher, similar to what's implemented in Pentium 4-like processors. And this is data from my own paper, actually. Colors are not coming out very nicely, but the y-axis is micro operations per cycle. This is on an x86 processor model. Remember, x86 instructions are decoded into micro operations, RISC-like operations. And these are the micro operations per cycle on a 3Y processor. And these are a bunch of different workload suites. And these are actually the workload suites Intel used at the time to design their processors. So this is from a long time ago. But if you look at the average, this is the baseline performance if you don't use any prefetching mechanism. No prefetcher, no Runahead. Actually, there's software prefetching included in these binaries. If you use a stream-based prefetcher, you improve performance a lot. That's the difference between this blue bar and the black bar. If you use just Runahead and not prefetcher, you could improve performance, again, quite a bit. And if you use both prefetching and Runahead, which is the performance improvement of Runahead over prefetching, this is what you get, about 20% performance. Yes?
What's up when you're running a prefetcher versus when you're running a Runahead?
Say it again?
What's the prefetcher and the Runahead?
Oh, this is a processor that has both a stream prefetcher that we discussed and Runahead together. Whereas this bar has only Runahead but no stream prefetcher. Whereas the blue bar has only prefetcher, stream prefetcher, but not Runahead. So, basically, I guess one takeaway from this graph is prefetching, tolerating memory latency is quite important. Right? And I should have shown the perfect L2 bar here, but perfect L2 is somewhere around here, I think. It goes. You would gain an additional maybe 80% or 90% more performance if your L2 cache was perfect, if you will. And you can see those results in the paper that you're assigned. So another interesting comparison point, I think, with Runahead execution is how does this compare to increasing the size of your out-of-order execution window? So here there are 5 different machine models. The first one is a machine model with 128 entry instruction window. Remember, Pentium 4 was 126 entry instruction window. And you can ask me later why it's 126 entries. And the second machine model is if you add Runahead on top of a 128 entry instruction window. So that's the 22% performance improvement, I think something around that. Third machine model is 256 entry window. Fourth machine model is 384 entry, and the next one is 512 entry. So if you look at this, if you add Runahead on top of a 128 entry window, it performs better than a machine that has twice the window size, out of order execution window size. So you get, and the complexity of this is much higher. So that's another way of looking at Runahead, right? It's a prefetching mechanism that improves performance. It's a mechanism that gets the prefetching or memory level perils and benefits of a large instruction window, if you will. And these results are also in the paper that you're assigned. So this Runahead-based prefetching is applicable to in-order and out-of-order processors as well, right? There's nothing that says you can apply this only for out-of-order processors. You could use this for in-order processor as well. This is just to give you some idea of the relative performance impact of these different options, if you will, that we've discussed over time on some real workloads. Granted, these are memory-intensive workloads. So these workloads actually are workloads that miss in the cache sometimes. If there are workloads that do not miss in the cache, that are purely compute-bound, the results will not look like this. Okay? And you can see the paper that talks about how the workloads are selected. So there are four machine models again. This is the in-order machine model, in-order execution. Actually, it does contain renaming to eliminate, well, you know what renaming does, right? It eliminates false dependencies. So you could use in-order execution, in-order scheduling, and eliminate false dependencies to get a little bit better performance than using in-order scheduling without eliminating those dependencies. That's the first machine, and if you add Runahead on top of this, you get about, let's say, 40% performance benefit. The third machine is out-of-order execution without Runahead. So if you compare the performance of out-of-order execution, there's a significant performance benefit of in-order execution alone. Right? Okay? And the next one is if you add Runahead on top of the out-of-order machine. So this is the kind of curve you get, if you will, with the different techniques that we've discussed so far. So this is data from Sun. Chaudhry was an engineer who actually implemented, they called it scalp, if you will, scalp threading, Runahead on Sun Rock. And I guess once Sun was bought by Oracle, they don't have Sun Rock anymore. So this is not a processor that's out in the market today. But I wanted to show you this slide because it's illustrative of the trade-offs that we make as computer architects. This is, okay, let's see. This is the L2 cache size on the x-axis, and this is normalized instructions per cycle on the y-axis. It's normalized to some point here, I assume. And there are two processor models here. One curve shows the processor without Runahead, and the other curve shows the processor with Runahead. And this is the performance. So let's take one particular cache size, for example. If your cache size is 512 kilobytes, adding Runahead on top of that machine gives you about 40% better performance. This is this slide. But you could make a trade-off. You could design a machine that has 8 megabytes, if you will, 8 megabyte L2 cache size, but no Runahead. Or you could design a machine that has 1 megabyte L2 cache size with Runahead. If you look at the performance of these two machines, they're similar. Right? Which means that you can increase your cache size to tolerate memory latency, or you could add something like Runahead execution to tolerate memory latency. I guess which one would you choose? Well, you choose Runahead. So Runahead is more area efficient than caches, right? So if you're, and these are also again for particular workloads, right? These are for commercial workloads that they evaluated their machines on. So in this case, potentially you could choose Runahead. That's right. Because if you gain like 7 megabytes, perhaps you could use those 7 megabytes for some other things, right? Maybe you would put more cores on the chip. So these are the trade-offs, high-level trade-offs you can make when you're designing a machine. So if you look at, so it's this is what, in a sense, your simulator enables you to do. Okay. This is all simulation results because they obviously didn't design a machine with 64 megabyte cache and Runahead and without Runahead and tested all of these workloads, right? But if you have this curve and maybe other mechanisms as well. Maybe there should be prefetching somewhere over here, and I'm sure they evaluate it, but they don't show it here. Then you can make the trade-off. How big should my cache be? Should I employ Runahead, or should I not employ Runahead? Should I design in order versus out of order? Okay. And if you start with a 4 megabyte cache, if you add Runahead to it, I think it's 4 megabytes or 6 megabytes. I don't know exactly. But you can get the performance of a machine with 60 megabyte without Runahead, according to this. Okay. Any questions? Okay. So we've discussed some of the limitations of the baseline Runahead, and I'll iterate these again, just so that you know there's no perfect prefetching technique. But there are potential solutions to some of these, and I'll ask you what you could potentially do to solve these problems. We talked about the energy and efficiency problem, right? Not only Runahead, but any execution-based prefetcher executes instructions to do prefetching, which means that you can execute a large number of instructions speculatively without gaining any benefit. Now, there are techniques you can have to avoid these. Well, let's take a look at that. So the efficiency problem, I'll just give you some data. These are some spec CPU workloads. And this is average results, if you will. This is the increase in IPC performance due to Runahead, 22%. And percent increase in execute instructions due to Runahead, 27%. Maybe it's not so bad, but if you look at some workloads, you actually execute 60% more instructions to get maybe 5% benefit, performance benefit. Some other workloads, you actually execute 50% more instructions to get 0% benefit. So you're basically making your energy efficiency terrible, right? Some other workloads, you get a lot of benefits, like 235%, well, you almost double the number of, well, more than double the number of instructions you execute. Right? So this is not a good thing overall. So you actually, we've analyzed why this inefficiency happens, and there are 3 reasons I will not go into detail. Sometimes, for example, the processor enters Runahead, stays in Runahead 20 cycles, and gets out. Not good, right? Because you're not making a lot of progress. Well, why would this happen? This could happen because you have another prefetcher, right? Prefetching data. And a cache miss happens, and the prefetcher already prefetched that data, and it only takes 20 cycles for the cache miss to come back. That means you probably shouldn't enter Runahead in that case, right? And there are also cases where Runahead is just useless. There is no miss to be found later on, because the misses are dependent on this current miss, or because the misses are far away from each other, right? You have to execute maybe 1 million instructions to get to the next miss. Maybe that's how your program is. Mm-hmm. So if you can identify these, this is what you would get. You can do. And that's there are techniques that will help. You can read this paper if you're interested. You can actually reduce the number of executed instructions, extra instructions, to only 6%, while without reducing the benefit. So for this application where you were not gaining anything, you basically eliminate entry into Runahead. Okay. Any questions? I'll let you figure out some of these techniques. You can think of some of them also. Yes?
Are there other techniques that we could use to counter the increased power utilization? Maybe lowering the clock speed or something if the loads are low.
Mm-hmm.
So counterbalance this energy.
Lowering the clock speed when you stall the machine, when you're waiting for a cache miss, you could do that. Yes, you could do that. But that's orthogonal to this, right? So there's a trade-off. If Runahead is useful, maybe you don't want to lower the clock speed, right? Because you want to execute further. Yeah.
But maybe not at this time, right? When you save power somewhere else, when the loads are low.
I see.
And we use the power here.
Potentially. So if your loads are low, you may not want to reduce your clock speed, though, right? Because that's where you really need the frequency. So maybe some other time, when Runahead is not beneficial, you could do that. Okay, let's take a look at the other problems. This is the problem of dependent cache misses. I guess I should have replicated the slide. And this is kind of obvious, right? If you have a load that's dependent on a cache miss, you cannot compute its address. And this is true for any pre-execution-based prefetching mechanism. Like if you get a cache miss on this pointer, you cannot prefetch the next pointer. You have to wait for that. Right? So what is the problem specific to Runahead? You get a load miss. The processor enters Runahead mode. In Runahead mode, it executes this load 2, and it turns out load 2 is dependent on load 1. And it's marked as invalid. It cannot compute its address. It means that Runahead mode ends. Later, you re-execute from load 1. And now load 2 is encountered. Now you can execute load 2, right? Because its address, the value it's dependent on, this load 1's result, is available now. Make sense? Now it turns out it's a miss. Well, so you go into Runahead again and do Runahead execution. Now this is probably not good, right? Yes?
So in the paper, I think you said that if you have a miss, then you're just going to remove it from the instruction window. So that seems to be in contrast to when you get your first miss, where you wait until it gets to be the oldest instruction in the window and then remove it. So I'm sort of wondering why you chose to do that. Like, let's say that I have a prefetch and the data for this miss is going to be available soon. So in that case, might it be a good idea to keep it in so that...
Potentially, yes, you're right. Potentially. But that's... then you need to figure out when the miss will come back.
Or could you just wait until it gets to the head and then just remove it at that point?
Yeah, it is done at that point. All instructions are removed when they become the oldest. Yeah, all instructions are removed when they become the oldest. Otherwise, you complicate how you remove instructions from the machine. Okay. So there is a problem here, right? Because now you couldn't parallelize this cache miss. This wastes some opportunity to improve performance because you've done Runahead execution without any benefits. You also waste energy because of that. So if you do we did some ideal studies, and if you do ideal studies, if you could ideally, you could tweak your simulator somehow ideally compute this load's address. You could say nothing will be invalid in Runahead, potentially, and look at the performance of that in your simulator. If you do those studies, performance would improve by about 25% if you could do that ideally. Okay. So now how would you do it? We've already seen some mechanisms to potentially prefetch this load. Any idea? Predict the value. There you go. You could predict the value. And I'll let you figure out how to predict it. The idea is if you want to parallelize these two misses with a low-cost mechanism, you can predict the value of this L2 miss load. But you don't want to do it for all loads, perhaps, because only some loads actually lead to other loads computing their address. Let's call those address loads. And I'm not going to go into detail, but you can design a selective value prediction mechanism that predicts the values of these pointer loads. And you can read this paper to do that. So why is that good? Well, if you value predict this load 1 miss, now load 2 can execute. And if your prediction, it can compute its address and generate its miss. Now you can parallelize these two misses. And if your prediction was correct, at least at the cache block level, at least if this load, when you execute that, brought the cache block that it actually needs in correct execution, then this load will hit. Right? So you save cycles, you also save speculative instructions. That's because the processor doesn't enter Runahead mode again. Make sense? So if you would like to learn about how to do this, you can read the papers. I'm not going to go into the detailed mechanisms, but there are interesting low-cost mechanisms that allow you to predict the value of loads that load addresses. It's not an easy problem because, remember, it was hard to prefetch pointers into our cache. Now we're trying to predict the pointer's address. And we're trying to be even a little bit more exact because we're trying to predict this particular pointer that's being loaded. So it's not easy. So if you predict, if you have a zero value predictor, if you will, that predicts the value of a load as 0 always, that will not work too well in this case, right? Now you're predicting that the pointer that's being loaded is null. Sometimes it could be okay, actually. But, okay. So these are the readings. This is your required reading, but if you're interested in this topic, which is, I think, a very exciting topic. Well, for obvious reasons, I've done my PhD on it, but you can read these papers. But this is the only paper that you're really required to read. It looks like at least one of you read it. Well, actually, two of you read it, I think. I know that. Okay. Any questions on Runahead, execution-based prefetching? Pros, cons? Yes?
Yeah, so I have a question about prefetching in general, where if you reference a page that's that like doesn't exist, like what happens? Like how do you handle exceptions?
So in current systems, they're not handled. Basically, if you get a page fault, the prefetch is dropped. In fact, in many processors, if you get a TLB miss, the prefetch is dropped.
So is this similar like in Runahead mode? If I like divide by 0, does the register just get marked invalid? What happens?
Oh, in Runahead mode, yes, you could do that. In Runahead mode, you could mark the register as invalid. But in general, if you have a stream prefetcher, for example, let's say the cache block doesn't exist. Actually, a lot of the stream prefetchers today work on page boundaries. They don't cross page boundaries. Because you don't know what page that belongs to. Right? If you have large pages, that's not a problem. 1 gigabyte page or 1 megabyte page. Okay? So that's the beauty of speculative execution, if you will. If you're unsure about something, if it's going to affect correctness, you can just drop it. Because it's all speculative. You're not doing it for real. Okay. And that's how existing processors are designed, as we discussed, right? Prefetch instructions. Well, if there is no space in your memory controller to insert another prefetch request, drop the prefetch request. It's easy, it's simple, it doesn't add more complexity to the system. Yes, one last question, quick.
So if you go into speculative Runahead mode, and then you start like generating a request, like for the prefetcher, so like I plus 4, I plus 8, and then you come out of it, and then you start generating that again. Does that confuse the prefetcher? Because now it seems like I
That's a good question, actually. You're taking away my exam questions. I'm just kidding. That's a good question. It could confuse a prefetcher. So what a lot of prefetchers today do is they filter out some of the requests they've already seen recently. So if you've seen I plus 4, I plus 8, and you see it again, you don't train the prefetcher on those requests. Okay? Does that make sense? That actually already happens in prefetchers today for other reasons. Because when you have auto-order execution, you can have similar requests like that. You can have reordered requests as well. Okay, but that's a good question. That's a very good question. Shall we move on? Okay, let's move on to multiprocessors. It's another exciting topic, as I told you. These are the required readings, and these are the readings that you should hopefully do for cache coherence for the next lecture and for your lab assignment as well. Well, remember, this is a slide that we've covered before. This was a taxonomy of computers, Flint's taxonomy. Single instruction, single data, single instruction, multiple data, multiple instruction, single data, and multiple instruction, multiple data. We're going to cover this part now. Multiple instructions operate on multiple data elements, meaning you have multiple instruction streams that are executed. And multiprocessors or multi-threaded processors are like that. I say this parallel computers, but there's a reason for doing parallelism. I'll go over this very quickly. Parallelism is doing multiple things at a time, right? Things could be instructions, operations, and tasks. Main goal is to improve performance, but there are other side goals. You can reduce power consumption. If you can actually divide your program into multiple tasks, you can execute each task more slowly, and you can still accomplish the same work in the same time, right? While reducing power consumption. Does that make sense? I think we've covered this before. You remember the slide? Yes? No? So the idea is, well, okay, if you divide your program into multiple tasks and if you can execute everything in parallel, you can obviously improve performance, right? But if you divide your program into, let's say you have 4 n units, you can run each of them at a slower frequency. You don't change the execution time. Let's say you can perfectly parallelize your program. But because now your units are consuming less power, because you've divided the frequency by 4, you can also reduce the voltage. Remember? Remember the power equation we talked about? And this is actually one of the arguments that I've been given for a long time for building multi-core processors, if you will. You can do things more efficiently that way. Let's see. Power is equal to CV squared F. Right? If you reduce your frequency, you don't need that much voltage to supply to drive those transistors to run at that frequency. So you can reduce your voltage too. So you can cubically reduce your power, if you will. There's a cubic relationship between frequency and power. Right? So instead of designing one processor, you can have, if you will, 4 processors, 4 wimpy processors, if you will. This runs at F. Each of these run at F divided by 4. And you parallelize your program perfectly, such that let's say this is, what did I say over there? 4 n units, if you will. Let's say your program takes 4 times. This takes 1, 1, 1, 1. 1 unit goes to each. Okay. Now these two things finish at the same time, assuming ignore the memory for now. These 2 processors finish at the same time, but this is a lot more power efficient, right? So if you, let's plug in the numbers. Here you have, assume the capacitance remains the same. Assume the activity factor remains the same. Here you have V squared F. What do you have here? V divided by 4 squared times F divided by 4. Right. Is that true? Yeah. Yeah, assuming voltage scales with the same frequency. That's right. I'm giving you that's a very good point. Okay, I'll give you this. How about V divided by alpha squared times F divided by 4? Still, this is a lot more power efficient, I would argue. So that's parallelism actually gets you significant power efficiency. Now, there's another big assumption here. The assumption is that you can divide your program perfectly, right? And that doesn't introduce some other overhead. And that's the challenge. That's the big challenge of parallelism. Can you actually do that perfectly without introducing additional overhead? Because once you introduce additional overhead, that overhead eats away from the savings that you would get from here. And a lot of parallel computer architecture, the design of parallel computers, is about reducing that overhead. How to do this, how to design this computer such that it can execute the parallel program more efficiently, or you can parallelize the program efficiently while minimizing the overhead. So we'll discuss some of those sources of overhead right now. But if you're interested in something like this, parallel computer architecture is the course to take. The entire course is pretty much dedicated to how do you reduce that overhead. Okay, other goals, of course, are you can improve cost efficiency, scalability, and reduce complexity by designing a parallel computer or multiprocessor, if you will. Right? You can. Why? Well, hopefully these are simpler also, whereas this is harder to build, right? Which means that hopefully these are more scalable as well, right? You can put many, many more of those, assuming for a given power budget, right? And perhaps these are more cost efficient too, right? Because they're easier to build. So your time to market could be shorter. Again, the issue is this all works nicely if you can parallelize nicely. And you can also improve dependability if you have more of these things, perhaps you couple some of them, right? Remember the dual modular redundancy that we talked about? If you have one of these things, one of the powerful engines, well, you need to build another one to provide redundancy. Whereas if you already have these simple ones, maybe you have some modes where you operate these in dual modular redundancy mode. They execute the same program and you check the results. So parallelism also enables. It says dual modular redundancy is a form of parallelism, right? You have two computers checking each other. Okay, so we've seen, I'm backing up a little bit, we've seen a lot of different forms of parallelism in this course. We're going to focus on this part soon. But just to remind you, instruction level parallelism, we executed different instructions within a stream in parallel. And the most basic thing we've seen was pipelining. And then we developed the concept of out-of-order execution, speculative execution, superscalar, VLIW, data flow. They're all forms of instruction level parallelism. In fact, something I'll describe here is a form of instruction level parallelism too, but I'll classify it a little bit separately. Data parallelism. Different pieces of data are operated in parallel, right? Single instruction, multiple data processors. In a sense, this is vector processing or array processing, and some things we can see potentially later if you take 742. In a sense, data parallelism is really nothing different from instruction level parallelism because you're executing those different instructions, if you will, operations in parallel on different data. It's really operation level parallelism, both of them. Except in SIMD, you're taking advantage of the fact that all of the operations are the same. It's a very efficient method of exploiting instruction level parallelism. Okay, so task level parallelism is different. Now you're dividing the program into different tasks or threads, dependent or independent, and they can be executed in parallel. Multi-threading and multiprocessing takes advantage of this. Well, how do you actually get task level parallelism? That's the key question then. You could do this, run many independent tasks, processes together. And that's what you do when you're running your laptops, for example. I like the virus checker example. Somebody's running a virus checker on your computer while you're trying to do useful work. Oh, okay. I guess let's talk about the first one. The more difficult problem, although this is I'll call this a more difficult problem, but this is almost as important, or potentially more important, right? If you think about the trends in computing today, like cloud computing. Cloud computing is many people can send their jobs to a data center, and all of those jobs can be executed together. It's like multitasking across the entire world, if you will. That's what, for example, Google servers do today. When you do a search, they're all independent tasks that are running in Google's data center. When you use other docs, online collaborative documentation, for example, e-commerce, they're all independent tasks from different users. Now, there is some dependency on shared data, right? There is certainly dependency, but it's not as strong, if you will. The consistency requirements of that dependency is not as strong. For example, when you do a search, sometimes you get different answers. It may not be important to you. Or sometimes, if you have your Gmail open in two different windows, they're not consistent sometimes, right? Because the updates are late. So this does bother you, but it's not critical for execution. Whereas if you get that wrong when you're solving a single problem, you can actually get a wrong answer. So that's the difference. So this is, I would say there's no difference in importance between these two different ways of generating tasks, but this is a harder problem to build a machine for, if you will. Okay. So partition a single problem into multiple related tasks. And we will see an example of this very soon. I'll let you partition the problem into different tasks. You could do this explicitly. The programmer can explicitly say, this is task 1, this is task 2, this is task 3. This is called parallel programming. And it's easy when tasks are natural in the problem, like queries. This actually could be a single problem. It's difficult when natural task boundaries are not clear, right? So if you do not know how to partition, if there's a lot of communication between different tasks, then this is difficult. Or you could do this transparently or implicitly. You could say, compiler, do this partitioning for me. Or hardware, do this partitioning for me. You give it a single problem, programmer doesn't do anything, writes program in sequential execution and sequential language, and compiler does all the job. Now that turns out to be very difficult also. Compilers and hardware have a hard time doing this. Okay, so if you run many independent tasks, this is easy when there are many processes, but it doesn't improve the performance of a single task. So if you care about the performance of a single task, you could design a multiprocessor that executes, partitions a single program into multiple related tasks. Okay, any questions? So hopefully these are easy. Have you guys covered these concepts before? At all? No. Okay, good. 213 doesn't extend to multiprocessing at all? So there was a little section in that book.
At the very end, you get the thread.
Oh, okay. So you get the threads all. So this is the concept of threads, basically. You have threads that are operating on the same problem. So there are actually two forms of memory processing. Multiple instruction, multiple data is a very general term, right? Multiprocessors. So there are multiple laptops you have here. Those are all multiprocessors, right? They're connected via a multi-computer network, if you will. So you can have loosely coupled multiprocessors. The key here is there's no shared global memory address space between one processor and the other processor. Which means that the processors have their independent address spaces. This is processor 1, this is processor 2, memory 1, memory 2, and this processor cannot reference this memory. When this processor references memory, it's always to memory 2. You can think of memory as partitioned, if you will, between these different processors, and they cannot reference. So this is essentially a multi-computer network-based multiprocessor. And the way they're programmed, if you want to take a problem and parallelize it across these, is what you need to do is you need to have program it via message passing. This is a programming model where processors communicate via messages. And there are many different ways of doing this, and we won't get into that in this course. But the idea is you have explicit calls that are made from one processor to the other processor, like send and receive, for communication. And that may be needed when you're actually, for example, you remember the histogram example that I gave in one of the earlier lectures? You want to get a histogram of the letters that occur in a book, and you partition the book into pages, and each processor operates on a page, and they need to communicate when they need to merge their local histograms. Right? So how do they communicate? Well, they don't share memory. So what you can do is you can have one processor send, oh, here are the number of A's I have. Take this processor and add it to your local count and send it to the next processor. So this processor takes that, adds it to its local count, and generates a message saying, okay, I'll send it to the next processor. This way, because there is no shared memory, you're not updating. With shared memory, what you would do is you'd have global count A, right? And when this processor has its local count, all it needs to do is say increment the global count by local count. And every processor does that. Right? Because they have a single global variable that contains the total number of A's globally, if you will. But now we don't have shared memory in this loosely coupled multiprocessor. So you need to send messages to each other to figure out what that global count is. Okay? Yes?
How do you handle disks?
Let's not get into that right now. There's a lot of issues related to this, but let's not get into that. We can talk about it later. So the key is message passing. That's how you program these systems. You can think of this as a distributed system. Right? You can, this processor, for example, one way of programming these machines is using remote procedure calls. You might have heard of that. this processor sends a message to processor 2 saying, execute this procedure for me. And that procedure could be adding, and execute this procedure for me. Procedure is add count to your own count. And the arguments of the procedure is the number of A's, B's, C's, D's, E, ... that are computed by this processor. And this processor takes them, adds those to its local count, and sends another remote procedure call to another processor that adds them to its own count. And in the end, all the processors, by calling each other, compute this histogram, global histogram. So you see, hopefully, there's some difficulty in programming these machines this way, at least for this particular problem. So tightly coupled multiprocessors, the difference is they have shared global memory address space. So instead of different memory address spaces, now this is a logical abstraction. There's no physical abstraction here. I'll just give you a logical abstraction. They both see the same memory. There is only a single memory. When somebody says 0, actually I should do this. When a processor references 0, that's the same location on all processors. Whereas here, you have 0, let's say n-1, and 0, n-1. You have multiple zeros. Except the 0 is in memory 1, memory 0, let's call it. Whereas this 0 is in memory 1, right? Okay? So this is the global address space. Traditional multiprocessing is shared memory multiprocessing. This is called shared memory multiprocessing also. And almost all multi-core processors and multi-thread processors are this way today. At least the mainstream ones. So why is this nice? At least for some problems, shared memory is nice, right? So if we had this global count, we didn't need to program the machine with all of these remote procedure calls. You could just say, write the program such that this processor executes a program that says global count A equals my local count, well, plus equals my local count, right? And everybody does that. My local count A, right? So it's nice to program. The programming is similar, if you will, to a uniprocessor. Because that's what you would do in a uniprocessor, right? You would just add your local count to a global count, or temporary count to a bigger count, if you will. So it's like a multitasking uniprocessor, in fact. Because you can have multiple threads that are multitasked on a uniprocessor. And if you have the shared memory. Except the operations on shared data require synchronization. Right? So if you have global count A and everybody tries to increment A, and if that's not an atomic operation, now you'll get garbage at A, if you will. This global count A. So that's the difficulty. That's where the difficulty arises in this kind of processor. They have the same global address space. They share memory. But when you operate on shared memory, you've got to ensure that the data integrity at a semantic level is maintained. You don't change the programming semantics because you did not protect the data. And that's why this is called synchronization. Basically, access to shared data needs to be synchronized by the programmer. And we've seen critical sections, for example, and you have seen critical sections, hopefully. These are sections, code that protects the data that should not be updated while another processor is reading it or writing to it. They enable mutual exclusion. Only one processor writes the data while another can potentially write or read to it. Okay? This issue doesn't exist, if you will, in the loosely coupled multiprocessors because they don't share memory space. But now potentially for some problems, programming could be harder. For others, perhaps this is a better programming model. And I'll let you think about some problems where this could be a better programming model than this. Maybe this programming model is easy because we're used to it with a single program. Okay. Before we go more philosophical, let's look at some issues in tightly coupled multiprocessing. So I'm not going to talk about loosely coupled multiprocessing anymore. We'll look into some issues in tightly coupled multiprocessors. Well, I told you about shared memory synchronization. This is a key issue. So you need to somehow provide atomic operations to implement locks. We will talk about cache consistency. What happens if you have this shared memory space, but now processors cache the data? Cache 0, cache 1. I guess I don't get my numbers right today, huh? If you do processor 0 and processor 1, it should be cache 0, cache 1. So now if two processors cache the same location, and one of them decides to write to it, this data is stale now. So how do you ensure that the data stays consistent? That's the cache consistency problem. More commonly, it's called cache coherence. But it's really keeping the data consistent across multiple caches. Ordering of memory operations is another problem. What should the programmer expect the hardware to provide? Right. With a single thread, if you will, order is sequential order. There's no question about that order. Now, when you have multiple threads operating on shared memory structures, what should the programmer expect in terms of that order? Should the programmer expect the same order across different runs of the program? Or, another way of putting it, maybe that's too much to expect, but should the different processors see the operations in the same order? Maybe this processor sees the updates in a different way than the other processor, because there are delays in hardware. So, we will not cover this too much, because this is more of a later concept. But I'd encourage you to read the Lamport paper, How to Make a Multiprocessor Computer to Execute Programs Correctly. That's the IEEE Transactions on Computers, 1979. And we will briefly cover that in the next lecture. But take a look at it. It's 2 pages long. Okay, there are other issues when you have, actually these issues exist in tight, loosely coupled processors as well. The resource sharing, intention, and partitioning. Now these processors share resources, well, especially memory. How do you arbitrate access to memory? And we've seen this. We've seen how do you actually prioritize different threads when they access the memory controller at the same time, right? You had an exam question on this. Okay. Communication. How do you build the communication substrate such that these processors can communicate with each other, right? How do these caches get connected to memory? Do they have individual connections? Or do they have some other network, if you will? And we'll not get into this yet, at least. And load imbalance is another issue. When you partition your program across these, if you want to get the best performance, perhaps your program, perhaps you balance the work across these different cores, right? Across these different processors. Because if you do not balance your work, what will happen is this processor will execute, let's say, for 10 seconds, whereas this processor, you've given it a task because you partitioned your problem that way, that finishes in 1 second. Now you're not utilizing your processing capability well, right? Because this is going to go idle for 9 seconds, whereas you did not parallelize your program nicely, so you're actually using only one processor for 9 seconds. So these are all issues that will improve performance or affect correctness in tightly coupled multiprocessors. Just as an aside, before we move on to more multiprocessing concepts, we've already seen hardware-based multi-threading. This is also MIMD processing, right? Multiple instruction, multiple data. There, the issues are all of these, plus there are other issues. Now you're sharing even more resources, right? So when do you, if you have multiple threads in hardware, when do you switch between those two different threads? And we've seen different approaches to this, event-based, quantum-based, or more fine-grained approaches, cycle by cycle. Every cycle you switch to a different thread. And we briefly talked about simultaneous multi-threading. You can actually dispatch instructions or schedule instructions from different threads at the same time. Okay. So let's take a look at why parallelism is good. So let's take this example. I guess I should have done a subscript here. But this is a polynomial, and we have it to parallelize. So it's A4, X4. Let me write this more nicely here, if you will. You already have the question, so you can start to figure out how long it takes. A4, x to the 4, plus A3, x to the 3, plus A2, x to the power of 2, A1, x to the power of 1, plus A0. Now we're going to make some nice assumptions for multiprocessing. Assume each operation takes one cycle, and you have multiplies, and you have adds here. There's no communication cost between processors, and each operation can be executed in a different processor. You can do a multiply and add in a different processor. And a different processor can do only one operation. So how fast can you execute this with a single processor? And how fast can you execute this with 3 processors? That's the question. It's easy. For 3 processors or 1 processor?
1.
So 1 processor, 11. That's a good answer. Anybody else wants to do 11? How did you do the 11? You probably built the data flow graph, right?
No, I just started.
You started from 11 and built the data flow graph later?
So clearly you can get x in those cycles. You get x squared, you multiply x by x, so that's 1. If you get x cubed, we multiply x squared by x, so that's 1 more. If you get x to the 4th, we multiply x squared by x squared, so 1 more.
That's
so
right.
You have to do 1 for each constant and 1 for each plus.
That's right, yes. So I think it's like this. I already did it, I cheated. Yes, so you built the data flow graph basically in your head. So this is the data flow graph for this polynomial, if you will. And you have 11 nodes, and based on what I told you, 1 operation, 1 processor at a given time, it takes 11 cycles to do this. I could have built this more nicely. Somehow, this A4 should have come in right here, actually, that way. You have this A parallelism, and then you have X parallelism, and then you have additions here. But somehow I put A4 here. I don't know why. But this is 11, right? Everybody is on the same page with this. You build a data flow graph, and this is what you get. So what about 3 processors? It's a little bit harder. Parallelization is harder, right? Well, you need to use your notebook. Any guesses? Don't be shy. There is actually a point to this. Because I'm going to ask you to speed up. Yes?
Is it 10?
10. That bad?
I mean, there are only 11 steps.
That's right, but you have 3 processors. 7, getting better. I think you can do better. See, parallelization is hard, right? I guess that's the first thing. 11 is easy to get. Well, maybe what I have in mind is harder to get. Anybody bidding better than 7? Okay. Five. 5. Multiple people say 5. Looks like there's some convergence to 5. Anybody else? Everybody agrees with 5? Or this is too tough of a question to solve? I feel my exam questions were harder than this. You guys can do this easily.
Maybe they're also too hard to solve.
Okay. I don't think you're going to get me to ask this question on the exam by saying that. Okay. Anybody else? But I think 5 is a good answer. Well, how do you get 5? Let me show you. Basically, you factor x squared. You can do x squared here, and then you can do a3x and a1x. They can all be done in parallel, right? So 3 operations in parallel. That's the first prime step. And then you multiply x squared with a4, and then you also multiply x squared with a3x to get a3x cubed. And you can now add a1x to a0 at the very bottom here. So now 3 more operations per cycle. Well, now you have limited parallelism because you don't have 3 operations actually to execute in parallel. What you do is you compute this part. Oh no, this is the addition. Now you have a4x squared. And add, you factor out x squared, remember? Add a2 to it. Now you have a2 plus a4x squared. And then you can multiply that with x squared in the next prime step to get this plus this, if you will. So while you're doing that in parallel, you add the a3x cubed, a1x, a0. So you have all those 3, and then eventually you add that value to, what is this? a4x4, a2x cubed here. So it's 5 time steps. Is that how you guys got it? Or is there could be another way, potentially. You did it a different way? Okay. Yeah, I don't think you can do it less than 5 time steps. So this is how you get 5. So what is the speed up? Speed up is, remember, with a single processor execution time, what's called tau 1, equals 11 cycles. 3 processors, tau 3 equals 5 cycles. And your speed up is equal to tau 1 over tau 3, 11 over 5, so you get 2.2 speed up with 3 processors. So you don't get perfect speed up. Why? Because you cannot parallelize all the operations. That's the first thing to see. Is this a fair comparison? There, I did the same thing here. Were we fair to the single processor system and the 3 processor system? Let me ask it another way. Did we design the best algorithm possible to compute this polynomial for the single processor system and the 3 processor system? Which means that can we do better than 11 or can we do better than 5?
Definitely can't be better than 11.
Say it again?
You definitely can't be better than 11.
Are you sure? Anybody wants to challenge Eric? Or can you be better than 5? That's also a fair question, right? The question is this a fair comparison? Unfairness can come from because you didn't use the best algorithm for a single processor, or we didn't use the best algorithm for 3 processors, or we didn't use the best algorithm for either. So I will posit that we did use the best algorithm for 3 processors. And if you actually find that that's wrong, you can tell me. Maybe not the same algorithm, but the algorithm that leads to the best time. That's 5 cycles. And I will also say that we did not use the best algorithm for the single processor. We used the easiest algorithm for single processor.
Oh, because you can use like that, right?
Exactly. You can use, that's called something, right? Have you guys learned the Horner's rule, Horner's method? You could recursively factor out x, if you will, or iteratively factor out x. So a better single processor algorithm. This. You start with x, you factor it out, and then you factor out again, and then you factor out again, and then you factor out again. This is called Horner's method, Horner's algorithm. And if you want to read that, that's an old paper. And apparently he wasn't the first one to come up with it, but he was the first one to actually publish it, which means that he was really the first one to come up with it. Or actually put it in a way that is understandable for others. That's 8, exactly. Yeah. Yeah, it's 8. By the way, I have more respect for this paper after I visited the Royal Society. One of our major conferences was at the Royal Society this March, and it's a beautiful place. I did not see this paper over there, but it's a nice place. Anyway, yes, it's 8, and that's how you get it basically. You change the algorithm in the single processor by factoring out x iteratively or recursively, how you would like, depending on how you would like to look at it. And that's your data flow graph now with this new algorithm. And I would argue that this is the best algorithm you can come up with for this polynomial. And now your T1 is 8. So your speed up is actually 1.6 with 3 processors. So what's the point? The point is your comparisons need to be fair, right? Multiprocessing is not necessarily the best way if you can actually improve performance with fewer number of processors. So you can optimize your algorithm and get much better performance instead of adding another processor. So actually, if in this case it didn't happen, maybe I should come up with an example where it happens. But our speed up was 2.2. But there are cases where you can get speed ups that are super linear. As you add P processors, you get more than P speed up. This is called super linear speed up. Now that's kind of odd, right? Why would you get super linear speed up as you add some number of processors? Well, unfair comparisons is one way. Maybe your single processor algorithm was not optimized. Right? That's why you can get super linear speed up. So what's that super linear speed up? This is the number of processors we add. This is the speed up we achieve. Normally, if you can perfectly parallelize everything, you would get linear speed up. Right? If you're unfair, you could get super linear speed up. There are other reasons, actually. If you have caches, if you're adding caches also, or if you're adding memory as well as processors, now you can get super linear speed up. Because you're not adding only processing, but you're adding caching as well into the system, which means that your working set may start to fit in the entire space that you add onto the system. That's one reason to get super linear speed up. Is that a fair comparison? Maybe not. Maybe you should be comparing a single processor with the same cache size with P processors with the same cache size. Right? If you do that, then you likely do not get super linear speed up. So typically, speed up looks like this. And we'll see why it does look like this. But as you increase the number of processors, you get diminishing returns. You're at the sublinear space, and your returns are diminishing. But before we go into that, there are some metrics that I'll just quickly go over, especially with respect to this example. Looks like we still have time. Okay, utilization. So this previous example, basically utilization is how much processing capability we use. It's essentially the number of operations in the parallel version divided by how many processors you have times the number of time steps you've taken, basically. You can think of this as the volume of processing that you have and how much of it you actually use. Remember, you had 3 processors. We executed things for 5 cycles. But we didn't use all of the processors on all of the time steps. Why? Because if you go back to this, we did not execute 3 instructions here, we did not execute 3 instructions here, and we did not execute 3 instructions here. So if you will, these are the slots that were actually utilized in each processor in each time step. So here, our utilization is, we did 10 operations, whereas we could have done 15 operations. Our utilization is 66%, if you will. 2/3. So we're not utilizing all the processing capability, which means that we're wasting some of it. Redundancy, how much extra work do you actually do due to multiprocessing? And almost always you increase redundancy as you do multiprocessing. Well, how do we define it? Basically, the number of operations with P processors and divided by the number of operations with one processor. So if we go back to this, we had 10 operations in P processors, 3 processors. Here we had 8 operations. So we increase the number of operations. So it's 1.2 to get parallelism. And this is a fundamental trade-off. To improve your parallelism, you add redundancy. In fact, we did not add enough redundancy. We assumed some things, right? The processors can communicate in 0 cycles. So in real systems, there's more redundancy because they update shared data. Now you need to do more operations to synchronize for that shared data. So the fundamental trade-off is as you parallelize your program, your redundancy increases. You execute more operations. And here, it's 1.25, right? Efficiency is how much resource we have used compared to how much resource we could have gotten away with, if you will. So if you look at efficiency, basically, how much resource you could have gotten away with, basically this is one processor, you tie it up for the number of cycles that you needed. And in our case, it was one processor tied up for 8 cycles. Okay. So what is the bottom part? The bottom part is we tied up 3 processors for 5 cycles, if you will. So our efficiency was 8/15, which is relatively low. Okay. So ideally, if you want to design a good multiprocessor, you would like to maximize the utilization, minimize redundancy, and maximize efficiency. And if you've noticed, these 2 concepts are related with this equation. Efficiency is equal to utilization divided by redundancy. So you really maximize the utilization and minimize the redundancy, and you get the highest efficiency. Make sense? Okay. So let's take a look at the caveats of parallelism. Why do you actually get this diminishing returns, if you will? Why don't we get linear speed up? Well, remember Amdahl's law? That's why you're doing the reading, right? Because you have a parallelizable fraction of the program, and this is the single processor execution time. The multiprocessor execution time with P processors, you can get that by dividing the single processor execution time with P, which is where P is your number of processors. But this is applicable only to your parallelizable portion, right? Does that make sense? If you could parallelize your program perfectly, this is the performance you would get. So this fraction would be anywhere from 0% to 100%. For the non-parallelizable portion, adding more processors doesn't help. Right? It's just sequential. It's Amdahl's law. So if your alpha is 1, well, alpha is 1 means that your program is perfectly parallelizable. Then your speed up is T1 divided by T. And in this case, we kind of ignored, if you will, the communication costs. Okay? Okay. So if you compute speed up what is speed up? Speed up is really T1 divided by TP, right? T1 divided by TP, this is what you get. And this is probably the form of Amdahl's law you've seen. The fraction that's parallelizable divided by P plus 1 minus the fraction that's parallelizable, the fraction that's not parallelizable, and 1 over that. So as P goes to infinity, which means that as the number of processors goes to infinity, this term becomes 0, and your speed up is 1 divided by 1 minus alpha. And that's your bottleneck now, right? What fraction of your program can you parallelize? If this is 0.99, 99% of your program can be parallelized, well, what is this then? the best speed up you can achieve is 100. If 100% can be parallelized, then that's good. Keep adding processors. If 0% can be parallelized, well, you're doing something wrong by adding processors. Right? And this also depends on your algorithm, by the way. So that's why it's hard to do parallel programming. Yes?
Are there profiling tools that determine that alpha for a certain software?
For a certain algorithm?
Like, how do you go about figuring out what the alpha would be for?
Yeah, that's a tough thing. That's a tough thing. It's not very easy. Yeah. You could help. You could take help from profiling tools that could potentially help you. That's right. But this is, in a sense, this is more for analysis rather than figuring out an exact value of alpha. But if you do it, it could help. You're right. Okay. So let's take a look at how things vary with alpha. I think that this is very instructive the first time I saw it. So this is the x-axis. You vary the number of processors from 1 to p, while p increases. Y-axis speed up. What happens is, if alpha is 1, then you get linear speed up. I didn't show it here because my drawing is horrible. It would look pretty bad. But think about it, it's like this. Linear speed up. It goes that way. If your alpha is low, this is the curve you get. And regardless of what your alpha is, as long as it's below 1, you'll get diminishing returns. Meaning as you add one more processor, the incremental benefit you get from that processor is less than the incremental benefit you got from the previous processor you added. So that's why you get this curve. Now let's take a look at the curve in another way. This is alpha on the x-axis and speed up on the y-axis. And these are different p-values, increasing p-values as you go up. So the benefit is small until alpha is very close to 1. And I'll let you verify that. Okay? So that's Amdahl's law for you. And this is, to keep in mind, you should read this paper, that's why I signed it. When Amdahl wrote this paper, his point was alpha is actually small in many applications. So it doesn't make sense to build multiprocessors. That was his point in 1967. And that's why the paper is titled Validity of the Single Processor Approach to Achieving Large-Scale Computing Capabilities. He said, actually improve your single processor rather than building multiprocessors. Which is partially true in some extent, but there should be a balance. When you design your multiprocessor, you should never forget about the alpha. Okay. This is very fundamental. So people sometimes forget about the alpha, and 10 years later they remember, oh, this alpha actually exists. So what have we done? We've designed a throughput machine that doesn't handle the sequential portion well. So now let's handle the sequential portion well. Okay. So caveats. This is another way of stating Amdahl's law. I just changed the things here. F is parallelizable fraction, N is number of processors. One big caveat is the sequential portion limits your performance. Other big caveat, this is called the serial bottleneck. And I've told you about this in vector processors, right? This is exactly the reason why Cray 1 had the fastest scalar unit of its time. They did realize this at that time. They did realize that their performance was bound by this. And that's why they designed the fastest scalar unit. But the things are not as rosy on this side also. Meaning, is this true? As you add more processors, do you actually divide the execution time that's parallelizable by n? That's actually not true also. Amdahl's law doesn't capture that. And there's actually no similar law that captures this, but parallel portion is usually not perfectly parallel. Why? Because you have synchronization overhead. When you update shared data, processors need to synchronize. So as you add more processors need to synchronize. So your n is not actually dividing that portion well, because there are some portions over there that you cannot parallelize also. Load imbalance. If you had imperfect parallelization, again, well, where did it go? Maybe I erased it. Oh no, it's here. I had 10 seconds versus 1 second here, right? If you had parallelized your program this way, well, guess what? As you add more n, you're bound by this 10-second portion, right? So you need to be careful, meaning you need to minimize load imbalance. And there's a third part. These are the three fundamental issues that happen in the parallel portion. Resource sharing. Remember, we saw the memory scheduling. The processors need to access memory, and they get serialized because of bank conflicts. That means that you're not dividing your that perfectly parallel portion with N. Because now they're delaying each other. They're serializing in the resource, in the hardware resource. So these are the caveats of multiprocessing, if you will. Sequential bottleneck and the bottlenecks in the parallel portion. Let's just illustrate the sequential bottleneck. Yes?
We're at 15 minutes.
Oh, is it? We're at 15 minutes right now? Okay, you're right. This is actually 2:16. Okay, let me wrap up here. Actually, this is a good place to wrap up. So see, we will continue with this. I'll continue with the sequential bottleneck in the next time. But don't forget, whenever you design a multiprocessor, these are the parts that you should not forget. Or whenever you do parallel programming, these are the four things that you should never forget. Serial bottleneck, synchronization, load imbalance, resource sharing. And almost all parallel computer architectures, multiprocessor architecture, is about fixing these issues. Because these do determine your efficiency, utilization, redundancy, performance, everything. Okay, I guess let's go to the midterms. This is what you've been waiting for the whole lecture, right? Instead of multiprocessing.